look at two other classic Newtonian style problems I will also look at in class. Let's look at this example where we have some object that is on an inclined plane, that some angle, we call it theta. But this object just sitting here, if we're dealing with no friction, you know what's going to happen. This thing's going to start sliding down. It will accelerate down the plane. But why? Why is this? And can we predict for a certain mass what that acceleration will be? The answer is, of course we can. And the idea, you want to staple a little coordinate axis to this thing, and there's no reason your coordinate axis has to be up and down. We can just slap it onto this inclined plane and tilt it so that it goes down the slope. So we'll call down the slope x and perpendicular to the slope y. And if we think about the forces on this guy, well, gravity's going to be pulling, but it's going to pull straight down. It's always acting right towards the earth. It's not going to care about this slope. But what you're going to result in is that when gravity pulls like that, it means that some of it is pulling into the slope, something like that, and some of it is pulling down the slope. So you get these two components of gravity. This piece, this vertical piece, you could find, because this is a right triangle, you can decompose this vector. And so if f sub g is mg, we'll just write it that way, that would mean, since this is the adjacent leg to this angle theta, this would be mg cosine of theta. And similarly, this guy, since he's opposite that angle, will be mg sine of theta. So you have two little parts to gravity now, because we're on an inclined plane. Now the inclined plane's still going to push up with some normal force, something like that, but maybe you can just intuit from this diagram. Basically, this normal force is going to be equal to whatever this mg cosine theta thing is. They're going to cancel each other out. There's going to be no acceleration off the plane. It's not hopping up and down or anything. But you notice that this force, even though I drew it down here, it's actually acting right here, right? It's acting on this box, this whatever this thing is, and making it accelerate down the slope. So I've done my free body diagram. Now let me look at the net force, F net in our x direction equals mass times acceleration in the x direction. Let's say that's what we're trying to find. So what is that? Well, it's mg sine of theta. And mg sine theta equals m times the acceleration in the x direction. Turns out mass just goes away. It's on both sides of the equation. So my acceleration is g sine theta. Isn't that crazy? Now what's interesting about that is that the mass doesn't matter. It doesn't matter how big this box is, how much stuff in it. It could be elephants, or it could be mice, it could be whatever. And it's going to slide down with the same acceleration, which kind of makes sense, because in a air resistance friction-free world, everything falls at the same rate, and this thing is basically falling. It's just kind of falling down an incline. And in fact, if I make theta equal to 90 degrees, what happens? Well, we plug it in here. The sine of 90 degrees is 1, right? So then your acceleration just becomes g. So if I make this so that the box just falls, acceleration is g, it works. How about that? Now you can make this a little more interesting if you think about more of a real-world scenario. Let's say we get a snow day. Let's just go ahead and say we get a snow day. And you can't afford a sled. You just have a box, you poor kid, that you sled on, and you're going to pull this box up a slope, right? So you're exerting a force. That's not going to go blue. Okay, so you're gonna pull this thing up a slope. So maybe you're pulling on a little rope. We can call that tension, and you're pulling this box up a slope. So what are you fighting? Well, you got gravity. Gravity pulling down, which means that some of it goes into the surface, some of it goes down the surface. It's a right triangle. We could break that up. We also have the ground pushing back with a certain normal force. And you can actually look at this situation and say, well, now let's say I'm accelerating up the plane. So I can draw my little funky arrow like that and think that I'm going up the plane. So I can call that the positive direction as well. And think, well, what would an F net equals MA look like for this? F net equals MA. Since positive is up, I'm going to say tension minus, what is this piece? It's mg sine theta. Mg sine of theta equals MA. So maybe I'm interested in tension. Maybe I've got a little force meter, and I know what the tension is in the rope, and I want to know my acceleration. So we could solve for acceleration, and it's T minus mg sine theta over m. Now mass matters, right? It divided out here, but it doesn't over here. So you can imagine a lot of different scenarios where that's true. Now the last one we're going to look at is the classic and feared elevator problems. Oopsie. The elevator problems. You just imagine that you are inside of an elevator and what's true about you. So what I'm going to do is I'm going to draw a free body diagram of you. And I don't know if you ever notice when you're riding an elevator, sometimes it makes you feel heavy and sometimes you feel light, depending on what this elevator is doing. So really, what's going on? Well, what are the forces on you? Gravity is just the same. It's always going to be tugging on you the same amount, roughly, as long as you're on the surface of the earth. But this scale is going to exert a force on your feet. So, by the way, that's a scale. I didn't say that, did I? Like a bathroom scale or something like that. So F scale, pushing up. So there are scenarios where this might be longer, might be large. In fact, if you look at this free body diagram, if I'm going to accelerate in this direction, what needs to be true? I need to have a net force in this direction, right? Up. And right now it looks like these guys are balanced. These guys, if he's just sitting there, just minding his own business, the elevator's not moving, or if the elevator has got constant velocity, these forces are balanced. But if I try to accelerate up, I need a net force up, and this vector is going to be longer. And that's some of the stuff that we were looking at before. So there's a lot of different scenarios here. If you have v equals constant, if v is a constant, F net equals ma equals 0, that's just going to tell you that this scale, it's going to read your true weight. Nothing funky going on there. It's just going to read what's there. But let's imagine a different scenario. Let's imagine something more like this. Let's say we're going up, our velocity is up, and our acceleration is up. So we're going up and speeding up. Okay, what's that going to look like? Well, as you might imagine, if I draw a little free body diagram, my F scale is going to be bigger than my F sub g. I'm going to call it a positive direction. Okay, so if I do F net equals ma, I'm going to have F scale, F scale minus F sub g equals the mass of you, because that's what we're talking about, times your acceleration. And if I'm thinking about what is the scale reading, I'd say F scale equals F sub g, which is your weight, plus something, right? So here we see that if you're going up and accelerating up, say you're going to go to upper floors, it's going to read heavier. You're going to feel heavy. You feel heavy because the floor is pushing on your feet hard. In this case, the scale is, and you're going to feel heavy. But that's not the only scenario you can have. You can have a third scenario, let's say where your velocity is going down and your acceleration is down. Well, in that case, our free body diagram, guess what? Gravity's doing the same thing. It hasn't changed in any of this, but if we need a net force down, that means our scale force must be smaller than F sub g in order to go down, to accelerate down, to have a net force down. So I'm going to call down positive. Everything's going on in the downward direction, so I'm going to call that positive. F net equals ma again. So what's down? Fg. It's got the positive sign in front of it. I'll pull it out front. Minus F scale equals ma. Now if I solve for F scale, what happens? Well, it's got a negative sign, so I can bring that over to the other side, rearrange some stuff, and I think you're going to find that F scale equals F sub g minus ma. Look at that. So this is our weight. So if your weight minus something means you're going to feel light. And that's sort of like the elevator's dropping out from under your feet, right, when you're accelerating down. And so, you know, as you study this and you look more at this, you might want to try situations where your velocity is up and acceleration's down. What if they're different? Or maybe your velocity is down and your acceleration is up. You know, how does that change? What do you feel in those situations? So that was a big review. There's lots of other different types of problems. These are the main ones that we're going to focus on, and those are the ones that I wanted to give you a little more feedback on, so you can try some of these problems on your own.